Yes, class 12. In the last lecture we have done the Bio-Savart law. Now we will do the application of Bio-Savart law. The first application, if we have straight long wire of finite length, then what is the magnetic field near the current carrying wire? The first application is magnetic field near a current carrying straight wire. Suppose we have a current carrying straight wire having a current I through it, as it is of finite length, then we consider, suppose it is a AB wire. Then to find the magnetic field near this wire, we have the parameters which change when we change the position of point. Suppose we have to find the magnetic field at this point. The perpendicular distance of the wire will be A. Got it? If we change the point at this, but the perpendicular distance will be same, means this is not a parameter, the perpendicular distance, which change on changing the position. So we will take the another parameter, that will be angle from the end of the conductor. Suppose we have a point P here and it make angle phi 1 at the one end of the conductor and angle phi minus phi 2. As we have considered positive angle at the upside, then we will consider negative angle at the downside. Then at the second point, the angle make point P is minus phi 2, and this set of angle will change when we change the point position of point. On changing the position of point, the set of parameter phi 1 and phi 2 is changed, means these set is specific for specific point. Got it? Now we will find the magnetic field at any point in the form of phi 1 and phi 2. Got it? Now what we have? Consider a straight long wire AB of length L carrying current I. This is we have considered which is the source of magnetic field. Now we will consider any point. Let a point P near the wire such as perpendicular distance A and angle from ends is phi 1 and minus phi 2. This we have considered about the point. Now to find the derivation of magnetic field, as we have Bio-Savart law, and Bio-Savart law give the magnetic field due to current element, means a narrow magnetic field due to a narrow length having current, narrow length of conductor having current. So we will break it into the small current element and then integrate throughout the length, and to find the magnetic field due to the throughout the length, we will break it into the small current element. Suppose we have a small current element, as I have told it, that in the ideal DL tends to 0. it is very small, but for our convenient we will take as it can be considered and it can be shown on the board. So we have considered, suppose this length is DL. Got it? Now the angle for, as DL is a very small length, then I have taken the angle, this is phi. This angle is phi. This is the perpendicular distance, and always we will consider distance from the source as small r. Then we have considered this distance from the source is small r. Suppose it has length of L. I have considered length L. Then what we have? We have, according to Bio-Savart law, dB, a small amount of magnetic field due to a small length of current element, mu naught upon 4 pi IDL sin theta upon r square. We have these terms, but here we LDL will change theta. We have not considered, as theta is angle between R and DL. This is the angle between theta, but theta is not a parameter which change when we change the position of the point. So we will take this theta in terms of phi, as phi change, this R in terms of phi, and this DL in terms of phi. We will change these three parameters DL, theta and R in terms of phi. Let's check. As we have theta is equal to, we have to change theta into the form of phi. Here this is phi, this is theta, and this is a 90-degree angle, as this is perpendicular distance. Then what we have, theta plus phi is equal to 90 degree, and we have to take phi, we have to change theta. Then we will write theta is equal to 90 minus phi. This is the theta is equal to 90 minus phi. Then sin theta, I will write here sin 90 minus phi, or sin theta is equal to cos phi. Sin 90 minus phi is equal to cos phi. I will change sin theta into terms of phi. Now I will change DL and R. Here we have R, A, L in terms of phi. Then here sin phi is equal to A upon R. Then R is equal to A upon sin phi, or I will write here R is equal to A sin, no, I have write here cos phi, cos phi. Then it will be sec phi. These two parameters I have changed here. Now the third parameter is L. We will consider L in terms of phi. Then I will take here as tan theta. In place of theta I will take phi is equal to L upon A. Got it? Now L is equal to A tan phi. We need DL. Then differentiate this equation, we can find DL is equal to A as constant and tan phi is sec square phi. Integration of tan phi is sec square phi, and we have d phi as the parameter. On changing the L, phi will change. This is the third parameter we have changed. Now we will put in place of sin theta cos phi, in place of R A sec phi, in place of DL A sec square phi d phi. In the Bio-Savart law, put these value. Now d phi dB is equal to mu naught upon 4 pi I. In place of dl, I will write here a phi phi 1 phi 2 L. In place of dl, I will write here from here a sec square phi d phi. In place of sin theta, I will write cos phi. Cos phi. Then I have in place of r square, I will write a square sec square phi. Then this cancel out, sec square phi cancel out. Then we have dB is equal to mu naught upon 4 pi I cos phi d phi upon a. This I have. Now this is for only a small current element, but we have to find out magnetic field due to a straight current carrying wire. Then we will integrate to find magnetic field due to straight current carrying wire. Current carrying wire, or we can write here current carrying conductor, straight current carrying conductor. Then B will is equal to integration dB, write the value mu naught upon 4 pi I cos phi d phi upon a. Take the common term outside the integration, as mu naught will remain same until and unless medium between the around the current carrying conductor will change, mu naught will not be changed, upon 4 pi a and I. Now integrate cos phi d phi. The cos phi integrating we have mu naught upon I 4 pi a, and here sin phi, and the limit. Here the point P we have considered, and this particular P, phi will change for phi 1 to here minus phi 2. The lower limit is minus phi 2 and upper limit is phi 1. Phi 1 to minus phi 2. Here we have write minus phi 2 phi 1. Phi 1 minus phi 2. After integration we will put value minus phi 2 phi 1. Put the limit mu naught I upon 4 pi a, and upper limit sin phi 1 minus sin 2, and sin minus theta is minus sin theta, then it will become plus sin phi 2. This is the final answer. Magnetic field due to the current carrying conductor. Now we will consider special case if the conductor is of infinite length. If the conductor is then phi 1 is equal to phi 2 is equal to 90 degree, as if this point will increase, the angle between perpendicular line and this end will increase. See, this is the perpendicular distance, and on increasing the distance this angle will increase. And we will consider for infinite length phi 1 is equal to phi 2 is equal to 90. Put the value of phi 1 phi 2 in this formula. For 90, then we have B is equal to mu naught upon 4 pi I, and here we have A sine 90 plus sine 90. What we have? Sine 90 is equal to 1. Then it will become 2 and 2 cancel out to 4 by 2 times. Then we have B is equal to mu naught upon 2 pi I upon A. This is the formula for magnetic field for infinite current carrying wire. Infinite current carrying conductor. Straight conductor. Now the second condition, at the end of the conductor. Second condition. At the end of conductor, if we move at the one side of the conductor, this point, then the angle for one angle will change as increase, and angle for second angle will decrease on moving the upward direction. Then we will write phi 1 or phi 2, any one 0 and the second one 90 degree. As we move towards the one end of the conductor, one angle will gradually decrease and second angle will gradually increase. And at the last point, end point, we will consider and one angle is 0 and second angle is 90 degree. Put this value in this formula. We have mu is equal to B is equal to mu naught upon 4 pi I upon A and sine 0 plus sine 90. What we have? Sine 0 0, sine 91. Then final formula will be B is equal to mu naught I upon 4 pi A. Now, as B is the vector quantity and it will change according to the days. We have two vectors L and I, and the direction of B in the case of A cross B is equal to C. Suppose we have three vectors A cross B is equal to C, then definitely direction of C will perpendicular to AB plane. AB plane की perpendicular ही आती है हमेशा cross product में. And here we have two vectors resultant of 2 L and R in the direction of B. Then it will be, the direction of B will be on the perpendicular plane of L and R. Here we have L and R, and perpendicular plane will be into the board or outward the board. Then we will check this direction according to right hand thumb rule also. If we have straight current carrying conductor, then always we will take the direction of magnetic field according to right hand thumb rule. Suppose it's a current carrying conductor and I will hold it in right hand as the direction of current in the direction of thumb. Then the magnetic field according to the fingers, direction of folding of fingers. Then always we take, suppose the point is here, the direction is this. Point is here, direction this. Means always the direction of magnetic field perpendicular of the plane. Plane, ideal and R. This is the ideal and this is the R. Suppose the point is here, magnetic field perpendicular to this plane. Point is here, the magnetic field perpendicular to this plane. This plane ke perpendicular. Got it? This is the direction of magnetic field. And the other law, to find the direction of magnetic field for a straight current carrying conductor, always hold the conductor. Imagine the current carrying conductor hold in right hand and the thumb is direction of current. Then the magnetic field indicate the direction of finger. Suppose the direction of current is downward direction, then we will hold it at this. Then magnetic field will be